this lesson, we're going to be talking about mathematical expectations, and we're going to start with what is known as the mean of random variable x, or the mean of the probability distribution of x, or you may have heard of it as the expected value of the random variable x. In Chapter 1, we discussed the sample mean, which is the arithmetic mean, or the average of the data. Now we're going to consider the following. So if you think about if we roll a die, and each die has a 1/6 chance of outcome of 1 through 6, then the expected value of the roll would be 1/6, or the relative frequency, times each value. Okay, so for each value of rolling a die, we could have a 1, a 2, a 3, a 4, a 5, or a 6. We multiply that by its probability of occurring, so times 1/6, 1/6, 1/6, 1/6, 1/6, and 1/6. And if you take those values, multiply them by their probability or their relative frequency of occurrence, you end up with an expected value of 3.5. But we all know if we roll a die, we would never get a 3.5. But the expected value, or the mean of the random variable, or the mean of the probability distribution of x would all be equal to 3.5. So we'll look at another example. Okay, we're going to run an experiment, and we're going to toss 2 coins 16 times. And x, our random variable x, is going to equal the number of heads occurring. So we do this experiment, we get 0 4 times, we get 1 7 times, and we get a 2 5 times. So when we want to take a look at the average number of heads per toss of our 2 coins, we have 16 times, so a 0, its relative frequency was 4/16. It came up 4/16. And then our 1 came up 7/16. So this computation is similar to what we would call a weighted average, if you've ever done a weighted average before. And when we do this, for this experiment, for this data set, our weighted average would be 1.06 as an outcome. And you know, and you can see that 1.06 is not an outcome that we could get, but it is the weighted average of this data set, of this sample. So now, if we took, assuming that we had a fair coin, and we tossed it twice, and we wanted to find the sample space and the probability of each outcome, of what the expected value would be of tossing the coin 2 times. That is what is known as the expected value. And let's take a look at what that would be. So our sample space would be head, head, tail, head, head, tail, and tail, tail. That's our sample space. So for 0, we would have a 1/4, 0 heads, 1/4, that's what we would get tail, tails. For 1 head, we'd have a probability of 2/4, or 1/2. And for 2 heads, we'd have a probability of 1/4. So if we wanted to know what's our expected value, what's our probability of coming up, what's the likelihood of our outcome, we would do what is known the expected value. And the expected value of x is equal to, we're going to call that mu of x. And the x often is understood, so you just would see a mu. But that would equal 1/4 times 0 plus 1/2 times 1 plus 1/4 times 2. So our expected value of running an experiment of flipping 2 coins and finding the number of heads that we should get, our expected value for this experiment should be a 1.0. Now, on our previous experiment we ran, we had a weighted average of 1.06. So in the long run, if we continued to flip 2 coins, we would expect that our result would average 1. And that's what the expected value is. Okay, let's look at the definition of expected value. So let big X be a random variable with probability distribution f of x. The mean, or the expected value of x for discrete, so we're going to talk about discrete first, is mu is equal to the expected value of x is equal to the sum over all little x of little x times f of x. And then for continuous, we have mu is equal to the expected value of x. So whereas discrete is summation, continuous is integration. Is the integration from minus infinity to infinity of x, little x times f of x. Okay, we're going to look at this example of a discrete random variable of expected value. So we have a chart, and this is given the sales data for a car salesman. What is the expected income for each customer visit to the showroom? So we have the car and amount made per car X, the probability of a car sold f of x, and then this row would be our x times our f of x. So we have a luxury convertible, we make $400, an economy sedan, $220, no car sold, you don't make any. The probability of a car sold luxury convertible would be 0.03, economy sedan 0.12, and no car 0.85. So you'll notice that these all equal, this is our probability distribution, so it equals a 1.0. If you add 0.03, 0.12, 0.85, that would equal 1.0. So we want to calculate what's our expected income for per customer visit, because this is what happens. 85% of the time they don't buy a car, 12% of the time they buy an economy sedan, and 3% of the time they buy a luxury convertible, and these are the amounts made from each type of sale. So let's take a look at the expected value. So we would have, so our mu is equal to our expected value of x, and since this is discrete, we're going to sum, and we would have 0.03 times 400 plus 0.12 times 220 plus 0.85 times 0, and that would equal $38.40 per customer visit. And as you can see, nowhere on the chart is $38.40, but this is the weighted average, the expected value of what this customer visit to the showroom would equate based on the amount made per car and the probability of selling a car. Okay, now we're going to look at a continuous example. Okay, so we have x is equal to the number of hours of the life of an electronic device. So our f of x is equal to 20,000 divided by x cubed for x greater than 100, and then it is 0 elsewhere. So we want to find the expected value of the life of this device. So our mu is equal to the expected value of x, and remember, for continuous we do integration. So we are going to look at integrating. This is x greater than 100. So 100 would be our minimum value, and positive infinity is our maximum. Because remember, it goes from minus infinity to infinity, and we say that x must be greater than 100. So we're going from 100 to infinity. And then we're going to say the expected value of x is x, so there's x, times f of x. And f of x is 20,000 divided by x cubed. So you can't forget to put in the x times f of x. And then this is dx. So when we do this integration, you can follow it through, the expected value would equal 200 hours. So the result means that we can expect this type of device to last on average 200 hours.